This video is on measuring load balance efficiency when you have a parallel computer with lots of processors. So here's the setup. In this case, suppose we have 20 processors numbered 0 to 19, and each one has some amount of work. So here's the processor number here, and I gave them 1,000,000 units of work. And maybe these are users or particles or some work packet, some bit of work, and it's homogeneous in the sense that any processor can process these units of work. So you can shuffle the units around if you want. And we're looking at how should you measure the efficiency of the calculation. So one metric might be the minimum work divided by the maximum work. So in this case, since they all have the exact same amount of work, they all have 1,000,000 units of work, um, that gives you 100% for the minimum over max. And another metric, average over max, which I claim this is the correct load balance efficiency. And I'll show you that this metric is meaningless. The min over the max is meaningless. So in this case, it's perfectly load balanced, so it's not that interesting. But suppose we only give 1 unit of work to this first processor. So it doesn't really, it just has 1 unit of work, and all the other processors have 1,000,000 units of work. So if we look at the metric, the min divided by the max, that's 0.00001% efficient. Well, I won't even use the word efficient, but that's what that number is, 0.0001%. And the average over the max is 95%. So I claim that this metric is meaningless because if we were to perfectly load balance this calculation, like basically take 5% of the work from all of these other processors and move it over to the 0th processor, then, every processor would just go down by 5%. So the calculation would just finish like 5% faster. So the real notion of efficiency is the average over the max. And there's essentially no information in the minimum. Because remember, the definition of the average is the sum of all these terms divided by the number of terms. And so it's got the sum in there. So even if we shuffle things around and move things around, you can't change the average. Uh, so so this really the average is immutable as you shuffle given a specific workload, like some total amount of work. You can shuffle things around, but that doesn't change the average. But you can change the minimum. So the minimum basically doesn't control everything. It's really the maximum that matters. Now let's consider a different workload. Suppose I gave 2 million, 1, 2, 3, 1, 2, 3, 2 million units of work here. So now the most work processor has 2 million units of work. These 18 in the middle have 1 million units, and this uh, the least work processor just has 1 unit of work. Now you can see, and you have to wait. You have to stick around till every processor is done. So the total time is controlled by the most work processor. So it's really the maximum that matters. So this calculation is 50% efficient because really it should just take like up to here to finish, but we're waiting around for here. Like even if I make this, let's make this 1,000,000. 1, 2, 3, 4, 5, 6. So um, the real efficiency of this calculation, it's like 52% efficient versus if I make this just 1 unit, the min over the max is meaningless. It's not like if I were to take this 1,000,000 units of work and sprinkle it over all these processors, the calculation. In other words, the reciprocal of the efficiency should give you some indication of the speed up if it were perfectly load balanced. Yeah. So like this is if it were perfectly load balanced. So the reciprocal of the efficiency is 2. So that basically this calculation should run twice as fast if we took all this work and sort of sprinkled it over all the other processors. It would run twice as fast, but it's not going to run 1,000,000 times faster. Like so this minimum over maximum is a meaningless metric. like, and this workload like really demonstrates that. Um, you know, most of the processors have a million units of work, or one processor has just 1 unit of work, and one processor has 2 million units of work. So really, this calculation is 50% efficient because we could take this work and sort of sprinkle it over all the other processors. And yeah, even if I made this 1 million, 1, 2, 3, 4, 5, 6, yeah, this calculation is, yeah, it's 52% efficient because we take 2.5% of this and sort of sprinkle it here, and then everybody has the exact same amount of work. So the point is that this workload very clearly illustrates that the min over the max is a meaningless statistic, and that the average over the max is the correct load balance efficiency. So while it's sort of interesting to report the minimum worked processor, there's really not much information in there. You want to pay attention to the average. The average has a lot of information because that's the total amount of work. Even as you shuffle things around, you're not going to change the average. As you shuffle things around, you want to bring down the maximum. It doesn't really help if you bring up the minimum, or it helps very little. So you focus all your attention on the maximum. And I hope I've convinced you that the min over the max is a meaningless efficiency metric, and that it should not be used. And thank you very much.